All right, so now we're going to look at lab one. This is actually for marks. I'm not going to share my screen for the report portion, but I will share the code with you and try to explain the code for you. I'm going to divide this into two parts, one being the explanation and the other part being the explanation of the code. So the first part is the explanation of the just theory behind it, and the other part of the code, just to clarify that. So in the report, I'm actually gonna read it to you. So just because I think that that's better for me to remember and also make sure that I don't miss anything. So here we go. So in the world around us contains various analog signals, right? So as reality is generally continuous, these signals contain information that needs to be transmitted. The transmission of these signals must be done in such a way that improves the possibility that there will not be errors and data is compressed to save space. Yes, space is very critical nowadays. So we have to make sure we can reduce it and get rid of unnecessary data. In order to perform such functionalities, you must utilize devices such as computers. Of course, these devices, however, speak the language of binary, and hence the real-life signals must be digitized. The process of digitization is also known as PCM, or pulse code modulation, and involves three steps: quantization, first sampling, and lastly encoding. Sorry, I should have said it. But that's the order, right? So first you sample, then you quantize, then you encode. And we'll see what that means in the actual program there. In the first part of PCM procedure, known as sampling, we can mathematically represent this by a multiplication of the time domain signal with a certain delta function that has been shifted by nt naught. So it would be sigma t minus n capital T naught. Summation of that from n equals negative infinity to infinity. And this symbol is referred to as a delta function, is shifted by n T naught and summed with different values of n, where T naught is the sampling period of the inverse of the sampling frequency. Yes, because period is the inverse of frequency. This operation is converted into the frequency domain through what is known as convolution. Convolution is performed by original function's Fourier transform and the function below. So yeah, there's two ways you could look at a signal being sampled. You could look at it as a multiplication in the time domain, or you can look at it as a convolution if you converted that signal into the frequency domain. Why do we have such a thing where you have two different operations that result in the same output? Well, because sometimes convolution is very difficult to perform that operation, and therefore you need to convert in order to do multiplication. So it's just different ways of looking at the same thing and how you would generate the output. So this operation can be visualized in the time domain as the original function plotted with only points in it that it's sampled at. Furthermore, in the frequency domain, it can be visualized as copying the signal infinitely many times from negative infinity to infinity with n times the center frequency of the signal. So you would see replications of the signal. When designing a system to perform sampling, one must take into consideration the sampling rate and the following restrictions. You can't just sample at any rate you want. There's actually a condition that is used so that we don't get a phenomenon known as aliasing. So we'll talk about that. Just hold on for a second. Sampling frequency must be greater than or equal to a frequency known as what's called the Nyquist frequency, which is 2 times the maximum frequency of the signal you're trying to sample. at maximum frequency value, maximum frequency value of the signal. Yes, in an ideal world, we can sample exactly at the Nyquist rate and reconstruct the signal with relative ease with what is known as a low-pass filter. However, filters are not ideal, of course, and hence it is necessary to sample at higher rates. The higher the sampling rate, the better. But another thing to keep into consideration is the processing time and the power consumption. Yes, so you can sample at higher rates, but there's no free lunch, right? In anything you do, there's always a restriction, right? The next step, once sampling is completed, is to create levels of signal value and map the samples to these values. The purpose of the creation of levels is that it gives an infinite set of possibilities for sampled values, hence allowing computers to receive a binary value for the sample corresponding to that level. Once the number of levels is determined, the number of binary digits per level can be found via the formula. L, which is the number of levels, is equal to 2 to the power of the number of bits you're utilizing. So we're basically sort of taking this seemingly random set of samples and we're categorizing them based on what level a particular sample maps to, so that we can have a discrete set of values and therefore can convert them into a binary representation for that particular level. And therefore a computer can store this information. And then if we wanted to know how much, we use that formula, which is L is equal to the 2 to the power of n, where L is the number of levels and n is the number of bits. And the quantization produces error E, of course, right? If you're going to map something, you might actually not provide the actual value, right? So because it's like rounding, right? So there is going to be some sort of error there, and therefore it is what is known as a lossy process. And it follows the following equation, which I'll read to you, which is E of t is equal to xq of t minus x of t, which is basically the quantized signal minus the original signal will give you the error. The error can be reduced with a higher amount of levels. However, this requires more data, yes, because you would have to store more information because there's more levels. More levels, higher amount of bits, things like that, right? Generally, quantization is done in a uniform fashion, which we call uniform quantization. So the process of categorizing things in terms of levels is what we refer to as quantization. So generally, it's done uniformly, meaning the levels are spaced equally. And the range between interval between levels is known as the quantization interval. That's the interval between the different levels. The value Q is dictated, which is a quantization interval, by the peak-to-peak signal voltage divided by the number of levels you wish to utilize, and hence the formula is Q, which is the quantization interval, is equal to the peak-to-peak voltage divided by the number of levels. Peak-to-peak meaning the max voltage minus the min voltage. And the last thing that's important to know, and they want you to know this, is that the maximum possible error that can occur in uniform quantization is between negative the quantization interval over 2 to the quantization interval over 2. So within that range, you can have error, and it's okay. After that, you will see signal being mapped to things that are to a whole new level, which will be pretty substantial of an error. General flow of the lab will be commenced as follows. First, the pre-lab is executed, which involves the sampling, followed by the programming of this. Thirdly, a voice signal is quantized via MATLAB at various quantization intervals and reconstructed. Lastly, the results will be observed and comparisons will be made between MATLAB and the calculated ones.